Alright, so in this section we're going to try to use power series to solve a differential equation. So how's this going to work? Here's a sample second order differential equation. By the way, you could solve a first order as well, but we'll focus on the second order. And the ansatz now is going to change a little bit. We're going to assume that the function y, which is the solution to the differential equation, the function p, and the function q, we're going to assume those are all analytic at the point x sub 0. Meaning what? Do you remember? That means that they are all represented or representable by their Taylor series. Good. So this is in particular the Taylor series at x naught. And so that is what we're going to do. We're going to, in theory, plug the power series in for p of x, plug the power series in for q of x, plug the power series in for y of x, and I wonder why we would do that. So we're going to convert all those to power series, and now you'll notice that theoretically q times y is a product of power series, which you could compute as another power series. P times y prime is a power series, right, which theoretically again you could compute as a power series. And so you have three power series in your differential equation, and you want to combine all of those series into a single series. I wonder why we would do that. If we do that, we're able to solve for the coefficients of y of x, and we'll see that in the next example. Okay, so things can get a little bit messy algebraically. That's why I'm doing this on a slideshow instead of by hand, so that you don't have to wait as I write all this stuff out. So I should tell you that sometimes in class it takes 20 minutes to do one problem. Okay, so that's why we're kind of going through it here on a slideshow. Okay, so let's I guess we're going to do a big picture first. Substituting the series into the differential equation will give us something like 3 series equals 0. We're going to write that in a new form. And so this is the idea behind this polynomial. This polynomial is equal to 0 for all x. Let me say that again. This polynomial is equal to 0 for all x. Therefore, the coefficient in front of each of the x's must be 0. Okay, and so therefore we can solve for each of the coefficients. So we can set each of the Cn equal to 0 for each n. Okay, so that's our goal. This is kind of the intermediate goal then, is to write things in a single polynomial equal to 0, and then we set the coefficients equal to 0 for each one. All right, enough theory. Let's get down to work. Oh yes, I wanted we're just about ready. So if this is my ansatz, then how do I differentiate this with respect to x? The n comes down front. I get an n minus 1 at the top for my power. But notice that, remember, the first term of the power series is a sub 0 by itself, which is a constant, and so the derivative knocks that out. And so that's why we're starting with n equals 1 here. Okay, so the first term of this derivative then is a1 times x minus x0 to the 0 power, or just a1, right? So a0 is set to 0 because of the derivative. Good. Similarly, if I take the second derivative, the n minus 1 comes down, right? And so then I have n times n minus 1, a sub n times x minus x0 to the n minus 2. And notice again, the a1 up here, the first term, went to 0 because it was constant up here. So this power series starts with 2 times a2, right? a1 is gone, a0 is gone, and so this starts with a2, or 2a2 I should say. Good. All right. And so what we're going to do then is we're going to substitute these three expressions in. Notice that what we're doing here is we're replacing the unknown function y of t by the unknown power series, which means now the a sub n's are the unknowns, right? So if we were able to compute the a sub n's, we would know our solution. Good. Okay, let's see how we I just wanted to mention too, you could start this at 0, right? You saw that in some of our algebra, because the first term would just be 0. And similarly, in the second derivative, you could start this at n equals 1, because that would be 0, or n equals 2. Oh, sorry, not n equals 2, but n equals 0. So we have some flexibility in where we want to start the index. Okay, now we're ready to go. Okay, let's get started. So here's our first second order differential equation. We'll do the Maclaurin series. So that simplifies our algebra a little bit. Substitute. Do we all remember the goal? We want to write this as a single summation. And so before we do that, we need to simplify the algebra a little bit. Let's bring the x in here. Okay, and so we bring the x in. Good. And now we have our sum set up. And now we check to see that the leading power of x they all match up. They all need to match before we can go on to the next step. So here, if I plug in n equals 2, I get x to the 0 power. Here I would plug in n equals 1, that would be x to the 1 power. Here, this is x to the 0 power. So the first and the third match, but the second does not match. However, I could take this, remember we were saying, you could take this and start it at n equals 0 instead. And so that's what we'll do. Good. And so now we can make some substitutions. So what I'm going to do is I'm going to substitute k equals n minus 2 here for the first term. I'm going to substitute k equals n for the second, and k equals n for the third, right? And I'm going to rewrite my sum in terms of k. Okay, and so remember, if I put in k equals n minus 2 here, this is going to start with a k equals 0. So I'm going to be able to write everything. Oh, I guess I did have that extra step. K equals 0, that's how the first term. So this, by the way, is all this k sub 2 here. This is all in the subscript, right? If that's hard to read. So that's n changed to k plus 2, so that's k plus 1. That's a sub k plus 2 x to the k minus k a sub k x to the k minus a sub k x to the k. Good. Now I can write it as a single sum. And you could actually skip this step if you wanted to. You could jump from here to here once you get used to it. Okay, and so now I've got my goal. I've met my first intermediate goal, and that is to set a single polynomial sum equal to 0. Good. Does everybody see how we did that? I did a little bit of simplification here, right? So this was minus k a sub k and minus a sub k. So I factored the a sub k out and the minus out, and that left me with a k plus 1 between the two terms. Okay, so I did do a little bit of algebra there. Okay, and because this polynomial is equal to 0 for all x, right, that means that the coefficients must all be 0, and that's how I solve for my coefficients. Now I can set those coefficients equal to 0. And this equation now must be true for k equals 0, k equals 1, k equals 2, k equals 3, k equals 4, and so on, right? Good. So let's go ahead and solve that. I get the k plus 1's cancel, and I'm left with a sub k plus 2 is equal to a sub k over a k plus 2. Excellent. So this is called a recurrence relation. And so typically what we're going to do is we're just going to stop here once we get our recurrence relation. But because this is our first example, I want us to see how we would solve for our coefficients, a sub n. And so because we said that this was true for k equals 0, k equals 1, k equals 2, k equals 3, let's go ahead and just plug them in. What happens at k equals 0? Well, that means that a sub 2 must be 1/2 a sub 0. And now I plug in k equals 1, and I get a sub 3, and a sub 3 must be 1/3 a1. And now I plug in k equals 2, and I get a4 is equal to 1/4 a2. But a2 is equal to 1/2 a sub 0, so therefore I could write a0 or a4 in terms of a0. Good. And the last one we'll look at here is k equals 3. That's going to be, plug that in, you get a5 equals 1/5 a3rd a3, but a3 is 1/3 a1. So plug that in and we get 1/5 times 3a1. Now what I want you to notice is that all of the coefficients we're writing in terms of a0 and a1. Do you remember why that would be? Why would that be true? Well, the reason that's true, or that's what we might expect, is that a0 is actually the initial position and a1 is the initial velocity, right? So a0 and a1 are actually our initial conditions. And so what we're doing then is we're rewriting our solution in terms of the initial conditions, right? And so that might have been expected then. And so just continuing, let's just go ahead and here's what we were after, right? Our y of x. And so if I just do some regrouping of terms, in this case the terms with a sub 0 split apart from the terms with a sub 1. And so the terms with a sub 0 were 1 plus 1/2 x squared plus 1/4 times 2 times x to the 4th plus dot 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 plus a sub 1 times x plus x 1/3. You can read that. I should note that what we're actually doing here is we're writing y of x in terms of a combination of two functions that will form a fundamental set of solutions, right? And they form a fundamental set of solutions because we can find the solution for any initial conditions, the initial conditions being a0 and a1. Good. Now I should say that the book goes even further, and they ask for you to try to guess what this common pattern is here that you're seeing in the parentheses. We're not going to do that because that can take a really long time, and it takes a lot of practice. So we're just going to stop there, and I think I'm going to stop the tape here, or the tape, showing my age. I think I'm going to stop the video here, and we'll try another. We're going to start with a clean start in a new video, so we'll stop there, and I will see you in the next video. We'll just do another example next time.